gas laws today. Is that in frame?
Yes.
Okay. And there are solids and liquids and gases. Solids have the least energy. They retain their size and shape. Liquids have more energy, so the molecules move over and around each other. They can change their shape. They assume the shape of any container they're put into, but the size remains the same. So it measures a cup, whether it's in a square container or a round container. And finally, a gas, and a gas doesn't retain shape or volume. It can be compressed or allowed to expand. For this reason, a gas will occupy a container's entire volume. Are you looking at that and making sure it's
Fine, Dr. B.
Okay. So gases spread out to fill available space, and this is a process called diffusion, and it occurs randomly. Random is the key word that you will look to relate to when you're taking your California Standards exam. They will ask you questions about how diffusion occurs, and the correct answer is the one that says it occurs through random motion. Next we come to pressure.
That's good.
Pressure is the force per unit area. But the cause of pressure is that molecules hit the walls of a container. If a gas is not in a container, we call it atmospheric pressure or barometric pressure or air pressure. Everything relates to what we call 1 atmosphere. 1 atmosphere is 1 kilogram per square centimeter. Or 14.7 pounds per square inch. Now what does that mean? If you're talking about 14.7 pounds per square inch, what that means is this. Do you guys know what a 1 by 1 is? Yes. Not a 2 by 4, but a 1 by 1. 2 by 4s aren't 2 by 4 anyway. I think they're 1.5 by 3.5 or something. Okay, 1 by 1 is a piece of wood. No, so consider you have a column of air that's a 1 by 1, and you're standing on the ocean shore, and we always compare at the edge of the ocean because the column of air, if you went up to the top of Bear Mountain at 8,000 feet, well 7,000 in the valley, 8,000 at the top, the column of air is smaller, so it weighs less. So everybody compares everything at the edge of the ocean. So you take a column of air and it's on the sand and it goes all the way to the top of the exosphere, and you pick that column of air up and you put it on a scales and it weighs 14.7 pounds. That's what we're talking about. That column of air. So on every square inch on the surface of your body, you have 14.7 pounds of pressure. That means if you're not smashed flat, you're pushing out with the same turgor pressure. You probably learned that in biology. We take you out into space and set you outside. You explode because you know you're still exerting 14.7 pounds per square inch outward, but nothing's pushing inward on you. I need to turn that toward me so you can pick it up. But okay. I want you to work with this a little bit, will you? Okay. All right. So the device we use to measure pressure is a mercury barometer. And here we introduce a new unit, millimeters of mercury. So we have 1 atmosphere is equal, and that's the standard, 14.7 pounds per square inch, or a kilogram per square centimeter, but equal to that also is 760 millimeters of mercury. So 760 millimeters of mercury is also 1 atmosphere and is also standard pressure. So the device we use to do that is called a barometer. So a barometer, this is a really, really simple barometer. It's a dish filled with mercury. It's open to the air, and you have a vacuum tube upside down over it. The pressure of the air pushing down on the mercury backs it up, this tube, to a height of 760 millimeters from the top of the mercury up to here. That's about 7 centimeters, so it's about like that. It's not a whole lot. 760 millimeters of mercury, therefore, is an atmosphere, which is 14.7 pounds per square inch, or 1 kilogram per square centimeter. And there are still more units. One of these little millimeters, here's 760 of them, is called a torr. So 760 torr is the same measurement as 760 millimeters of mercury. In addition, a French unit called a kilopascal, 100 kilopascals is equal to 1 atmosphere. So what I've created here is a conversion, put them all in one place. Everything's in one place, so you're going to box this in red and highlight. So we have 1 kilogram per square centimeter, 14.7 pounds per square inch. Here's our basic conversion: 760 millimeters of mercury, 760 torr, and 100 kilopascals. All of those are interconvertible. So no matter what unit you're given in terms of pressure, you can convert it to whatever they ask you for. This is not only boxed in red and highlighted in your notes, you're going to put it on the back of your 3x5 card that you have your 4 basic formulas on, so you can use it anytime during a test or calculations. Thank you, Jason. Now, what if it's not atmospheric pressure? Suppose that we're talking about the pressure of a gas that's trapped. I'll just set it on my desk. Thank you. For that, we use a device called a manometer. There are 2 types of manometers. There are closed-ended manometers, because if a gas has very little pressure compared to the atmosphere just backs the mercury up into the gaseous chamber. But if a gas, which is what we're going to look at, has a pressure close to the atmosphere, we can use an open-ended manometer, and that's the kind we're going to look at now. So here we have a U-tube, and this is supposed to have mercury in it. And I keep hearing people say, well, mercury isn't red. I know. I don't have a silver marker, so I had to use red. But if you put water in here, or mercury, or anything else, the 2 sides are going to be level if they're both open to the atmosphere. And let's say the atmosphere is exactly at 1 atmosphere, it is 760 millimeters of mercury. So suppose here we attach it to a gas chamber, we open the chamber, and the mercury does this. The gas pushes the mercury away and backs it up toward the atmosphere. That tells you that the gas is exerting more pressure than the atmosphere. So we would add the difference in the heights of the two columns to 760 to get how much pressure the gas is exerting. So how much pressure would this gas be exerting? Anyone? The atmosphere is 760. We're adding this difference in columns, which is 40. How much pressure is the gas exerting? 800. Example, here is gas B. This time when you open the chamber, the mercury is pushed toward the gas. That means the atmosphere has more pressure than the gas. The gas has less. So now we would take 760 millimeters, which is our atmosphere, subtract the difference in the columns, and this gas is exerting 720 millimeters of pressure. Do you have that down? Tell me when you have it down. And I'm going to go work over here at the sideboard on their temperature scales. Any questions so far? What we're covering today are your introductory concepts. So give me 15 minutes of your time tonight to go over your lecture notes. So the language seems familiar when we go into calculations, which should be tomorrow. Maybe a little bit today. Can I turn these on?
No.
These are the metals for the eutectic gland. Good. Tyler, are you done? All right, so far what we've talked about is pressure. Now we're going to talk about temperature. Pressure and temperature are the two things that affect gases and how much room they take up. So here I have 3 columns and they are filled with bromine. And I've decided that the bromine in all of them has gone this high. And this happens to be the dividing line between, for water, ice cubes and water and steam, solid, liquid, gas. This is water. Even if these were different temperature scales, the temperature would be the same. The temperature is the amount of molecular motion. So they all rise to the same point. If I carve different numbers in these, it doesn't mean their temperatures are different. The measurement of the heat might be different. A thermometer, a thermometer, is a heat measurer. So let's say, first of all, we have a thermometer or a thermometer in Fahrenheit degrees. Fahrenheit was developed in Germany, and freezing was very important because the rivers froze over and you didn't have commerce anymore. So that point was 32 degrees. And it's kind of an obsequious number. It's a little odd. And then boiling was 212. And then came Celsius, degrees Celsius. Anders Celsius was a Dutchman. And at that time they were developing the metric system. So he thought things should be in multiples of 10. So don't confuse the centigrade with Celsius. Anders Celsius was a person, and the centigrade scale means exactly what it says. Gradations are little notches or movements up. And if there's 100 of them, there's centigrade. There's 100 notches. So he started his freezing here. He went up 100 notches, centigrade, 100 gradations to boiling. Then they started doing experiments with exactly what is matter and energy, the beginning of particle physics, what happens if we lower it, how low can we go. Now look, if this is 100, 100, 200, 300, we can almost go 300 degrees. There's a lot more distance down here than there is the temperatures that we live at. And what they found is if you keep lowering the temperature, the matter disappears. You cannot have matter without energy. We've never reached this point, but they found that absolute zero, they believe, to be negative 273 Celsius. So when you get to that point, matter would be gone. And at that point, gradually matter comes into existence. We've never reached it. We've never gotten that cold. But it shrinks to almost nothing. But we cannot get to absolute zero, at least not yet. So then came Lord Kelvin. Lord Kelvin was British. He said, if you're saying that this is zero energy, why aren't we calling it zero? So he did. He called it zero. And then, using the same number of gradations, freezing became 273, boiling became 373. This is the only scale we can use in gases, is Kelvin. If you're given information in Celsius, you're going to have to add 273 to convert to Kelvin. Do you understand that? And we said that on these laws over here. Everything has to be in Kelvin degrees. Okay? So you're going to get this down in your notes. Now, turn it off for now. Nothing's going to happen until... I'm going to email the science fair to you again and then put that at the end, let it roll. And then for their lab, cut out the language and the camera movement. I know you wanted to, I know it said 2830, but it's, I think we cut out other pieces that could have, like the filing. There were a lot of...
We didn't want like 15 minutes of filing, did we?
If it's better than having it not 28 minutes and 30 seconds.
Okay.
Like if the choice is between having a couple minutes of filing or a couple minutes of camera swinging, the choice would be the filing.
Well, in between the filing is the camera swinging, so I mean we'd be under no matter what.
Let's see. Let's see. Because you got it really easy here. Have you got you brought both chips back? Okay. Have you got the little one? Could you lay it on my desk for you? Alright, so are we ready to start again? Mm-hmm. Is it on? Okay. Whether you're going to cut all this out. I don't want my instructions for you to be on there. So do we all have this? All right, so now we're going to talk in general about the relationship between solids and liquids with boiling and melting points. Boiling points and melting points are points where two phases exist together. And any energy that you put into a system when you have two phases will not affect a temperature change. You put energy into the system, but the temperature stays the same because the energy is used to change phase, not increase molecular motion. A liquid like water that's 100 degrees Celsius has the same molecular motion as the steam above it. For the period of time that you have both phases, the interface between them is at the same temperature. The boiling point for water, where liquid and gas coexist, is 100 degrees Celsius at 760 millimeters of mercury. If you have less pressure on the liquid, it will evaporate more easily. So we always have to define what pressure we're talking about. Melting point is where you have a liquid and a solid coexisting. And again, no matter how much energy you add, the temperature won't change. All the energy you're putting into it changes the phase, the state of matter, but the molecular motion doesn't change. Again, we define it at 760 millimeter mercury or 1 atmosphere pressure, and that is 0 degrees Celsius. To show this relationship, we have what we call a phase change diagram. Not only is a phase change diagram in your text and on your test for me, there's usually at least 2 questions on your California state exam at the end of the year. It shows the relationship between phases and how the energy that you put into the system is used. May I move this up?
Yeah.
Okay, let me talk you through this first. Is it clear? You see it? This axis is time. So we're adding energy, and we're adding more energy as time goes on, and this axis is temperature. So really, if we're assuming, of course, these are Kelvin degrees, well, no, it'd be Celsius because this is 0, but in terms of Kelvin, this would have to go way down to negative 273 Celsius or 0 Kelvin. This would come way, way down here to absolute 0. So since this is Celsius, we'd say negative 273, and gradually it comes up, and it's all ice, 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 ice. The temperature keeps changing, and then we hit 0 degrees Celsius. When we do that, and we keep adding energy, the temperature flatlines, it will not change. Because now the ice is melting. And as long as you have 2 phases, all the energy is going into phase change, not changing molecular motion, which is what a thermometer measures. After all the ice has melted, and you only have water, then the temperature will start to rise. Water, 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 all the way up to 100 degrees Celsius. When it reaches 100 degrees Celsius, the water begins to boil. And the thermometer doesn't change. It flatlines at 100 degrees. As long as you have water and steam in the same system, all the energy is going into changing phase. not into increasing molecular motion. Now, one point is the steam over the top of a pan of boiling water looks fairly innocent. But unless you're willing to put your hand into the boiling water, don't put your hand over the boiling water, because the steam is exactly the same temperature as the boiling water. They're both 100 degrees Celsius. So you have water and steam, and finally all the water evaporates, you have only steam, and now the temperature goes up. And superheated steam is very, very hot. So this axis is, as your water is heated, time goes on. This is your freezing melting point. Of course, this is your boiling point. Do you have any questions about a phase change diagram? And the next thing we're going to start talking about are gas law calculations. Can you focus that anymore? Is it possible?
It just looks small on the screen. It'll look fine on video.
Okay, I'm going to move this. Is that all right with you or not? No? Okay.
Bless you.
Thank you.
I'll email you that Oxford Oprah magazine. The first priority is the pending letter. So if you don't get to this, I'm probably just going to send out a system.
Like I said, I can't do anything today, but tomorrow I can.
So I'm going to send out.
Krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.